All right, last time we left off with doing a little bit of arithmetic inside of other bases. And we had taken a look at a problem in base 8. That one, yes? Okay, and we're going to do one inside of base 3. All right, so, and I mentioned I was going to try and do some of them where I did different methods. So there's nothing special about these methods in the sense that you're told what to do on these particular problems. Most of the time they give you great flexibility and you can choose which method you like to use, but occasionally they will tell you which method to use on a particular problem. So just pay attention to that. So on this one, we're taking a look at a base 3 problem, and we're reminding ourselves that we have the digits only 0, 1, and 2. Okay, so anytime we exceed that value, we have to go to a 2-digit number and so forth. And we're taking a look at the number 1, 2, 1, 2, base 3, and 1, 1, 2, base 3. And the last time I did a standard algorithm problem, I think. So, no, I didn't. I did a column addition problem. So this time, let's do a standard algorithm since we haven't done one of those with these yet. So we have the numbers that we're going to stack. And our standard algorithm says I start on the right-hand column, right? The ones place. So if I have 2 plus 2, I would actually get the number 4. But how would I express the number 4 inside of base 3? You're close. It's 1, 1. Okay, so if it helps to think about it, one of the ways to do so is you can continue the pattern at the top. 1 is 0, and then 1, and then 2, and then 1, 0, 1, 1, 1, 2. So that's one way to think about it. It's very similar to the counting up algorithm. So if I end with 2, I'm doing 2 plus 2, right? So after 2, I go to 1, 0, 1, 1. So I'm sort of counting on my fingers, kind of, or in my head in that perspective. The other thing that you can do is you can remember it's the number 4, yes, but if I'm thinking about that as broken down into the 3's place and the 1's place, how many 3's are in the number 4? Well, 1. And how many are left over? 1. Okay, so any of those are valid ways of adjusting that number in your head, but you should get the number 1, 1. So in the standard algorithm, we put the 1 there, and then we're going to carry the other 1 to the 3's column. Because what it really is it's 1, 3 and 1, 1. That's what the number 4 represents. Then we're going to do the same thing in the 3's column. So 1 plus 1 plus 1 is actually 3. How do we express that in base 3? 1, 0. So it is 1, 3 and 0, 1s. Now in the 3 squareds column, 1 plus 2 plus 1 is 4. We already did that one. We knew that that was 1, 3, and 1, 1. So that's the number 4. And then the last column, my 3 cubed column, is just the number 2. And anytime we write our answer, we really need to make sure that we write the subscript for the base beside it. Because with no subscript, we assume that that's a base 10 number. Okay, any questions on that? So that would be a standard algorithm approach to this particular process. All right, the next thing that we're going to take a look at is we're going to look at some mental math and some computational approximations. And so you're not going to do a whole lot of base stuff in this section, so I don't want you to be like freaked out. I mean, there's going to be a few problems. But the majority of it's going to be these algorithms used in our base 10 number system. So the last bit here is I want you to remember that the word mental does not mean approximate. Mental means in my head, okay? Approximation means that I'm going to be rounding something in some fashion, and we're going to be doing both, but sometimes people get those words confused and they use them interchangeably, and they aren't really meant that way. Mental math means I can do it in my head. That's good. And I want to show you some algorithms, some ways of thinking about doing mathematics in your head, and they're really cool. The problem is that I can't see inside your head. So you're going to have to write down for me what's going on inside your head so I can see it. Make sense? So while I realize it's sort of counterintuitive to ask you to show your work on your mental math, I don't know how else to do that. I mean, like we could meet one-on-one and we could have an oral test, but I don't think you'd like that either. So we're going to try it this direction, okay? All right, so this one is actually asking us to add from left to right. So we've seen this algorithm before. It's a lot like the column addition algorithm, okay? And so when we're looking at this, we're adding the digits in the left column first. So what we're really doing is we're saying, okay, well, I'm going to do the 40 plus the 30 first, which gives me 70. And then I'm going to add the 6 and the 8, which gives me, I hope it's 14, right? Yeah. And then 70 plus 14 is 84. Yep. Okay, so just doing it one place at a time. I don't have to worry about carrying, borrowing, any of that kind of stuff that happens with addition and subtractions. I'm just working one place at a time from left to right. Okay? Breaking up and bridging is a fun one. So the breaking up and bridging strategy, I'm using the same example for several times here, actually takes the second number, it could be the first number, but this one we're just going to do the second number, and it breaks it up into its two different components. So 38 is 30 plus 8. Okay? And what it does is it adds the 46 and the 30 together. Okay, so it's not exactly like single digit plus single digit addition, but the only reason it's not is because there's a 0 in one of the places that makes it double digits, right? The 0 and the 6 are going to add together so very nicely that they're sort of not, I'm not bothered by them, is the idea. So then the 40 and the 30 are 76. And then we add on the 8. And again, it is 2-digit plus 1 digit, which isn't super helpful, but it's 1 digit, not a 2-digit number at the end, which makes it a little easier to work with. And so I can add that, either counting up if you want to, mentally or whatever, but you're going to end up getting, of course, the same 84. So that's called breaking up and bridging. Okay, we've encountered this one as well. It had a different name. This one was akin to our opposite change algorithm. So if you'll remember with opposite change, the goal is to try to get zeros in as many places as I can because zeros are nice to add with. So we either add or subtract values to try to get zeros. So on this one in particular, like it's nice to add a 2 to 38. But if I add 2, the opposite change has to affect the other number, and so I subtract 2. So my 46 becomes 44, my 38 becomes 40, and I have 80. That is the opposite change algorithm. Okay, is everybody good so far? Kira? Why did I write 80? Because I don't know. I don't know why I wrote 80. Thank you. It should be 84. Okay. The next one is truly something that we haven't seen done before. It's kind of like what we talked about when we talked about making 10 last time, where we broke something apart, except it's easier. And I mentioned this strategy when we talked about making 10. So the idea is grouping things together to get tens or hundreds or thousands, something that's got lots of zeros. Get the idea that zeros are nice, right? We like zeros. So we're looking at a list of numbers typically with compatible numbers, and we're trying to pair them up in a nice way to add them. So while it's true that I can add from left to right, it's also true that I can manipulate things and add in a different order and it won't change my answer, right? Because 5 plus 2 plus 3 is the same as 2 plus 3 plus 5. So there's no reason I can't adjust to my liking. So are there any of these two numbers that you look at and you say, ooh, those are nice to add together? What do you see, AK?
70 and 30.
These are great. Yeah, these two add together to be 100 very nicely. What's another pair that adds nicely on here? Yeah, the 60 and the 40. Another 100. Now 50 is sort of left out. That's really okay because whatever's left out at that point is just one single digit because I had 5 numbers. Or not one single digit, but one single numeral. So I have 100 plus 50, which is 250. And that's easier than 40 plus 30, which gives me 70, plus 50, plus 70, plus 60, all because we just regrouped. And then the next strategy is like making tens. It's making compatible numbers. So you're doing the same sort of thing. You're going to break something apart into something that's much nicer to add to the other value. So, right, 35 is fine. What number would I add to 35, though, to get 100? That one's not quite as nice as 30. 65. So I take the 68 and I break it apart into 65 and 3, like that. Okay. And then these two add together to be 100, plus the 3, so this is 103. So you're just busting one apart into the value that sort of makes a nice 10 or 100 or 1,000, whatever, but a power of 10. Okay, so those are all different mental math strategies. As we go through the next sections of material, 3-3 is subtraction, 3-4 is multiplication, 3-5 is division. We're going to encounter this same structure where we look at what happens with these different ways of thinking about the mathematics, different models for the mathematics, all algorithms to do the mathematics, computational like this, mental math, and then also the next one, which is computational estimation. So what we're doing now is we really are estimating. So estimating means that my answers are not going to be precise. They're not going to be exact. The reason I think that this gets confused with mental mathematics is because we want to estimate in order to make the problem easier, often easy enough we don't need something to be written down to do it. But that doesn't necessarily mean that that's how we would, process through that. It doesn't have to be for the purposes of mental math. It just sometimes is. So one of our strategies with computational estimation is front-end estimation with adjustment. So there are two parts to this because of the two different phrases used here. There's front-end estimation, and then there's adjustment. So I think we've talked about front-end estimation before. Does it sound familiar or does it not? Nope. Okay, it's my other class. Sometimes I get confused. So front-end estimation is super friendly. It means I only consider the very first number and I ignore the rest of them. For the example, 332 is just 300. 462 is 400. And 225 is 200. So this is the front end part. So I'm just going to abbreviate it FE. That's front end estimation. Keep the first number, zero everything else out. And that gets you pretty close. I mean, it will be a fairly decent estimate already. So there is a method called just front end estimation. The adjustment part tries to take into consideration the other pieces that we just ignored. And what we do with those other pieces that we ignored is we try to make compatible numbers, or at least approximately compatible numbers. For example, 62 and 32, they're not exactly 100, but they're pretty close, right? They're pretty close. So we group these two together and we say that that's approximately 100. That's my adjustment strategy. And then you can leave the third number alone. If there's another number to group it with that you can approximate it to, fabulous. But if there's not, you just leave it. So we would have an additional to this 300, 400, 200. I'd have a 100, and then I'd have my 25. So these are the digits now, or the numerals now that I'm adding together. So 300 plus 400 is 700 plus 200 is 900 plus 100 is 1,000. So we have 1,025. And it's an approximation, right? So those squiggly braces or squiggly marks are a really nice one to do to remind yourself that. I didn't find an exact value, I found an approximate value. Grouping to nice numbers is another one that's basically compatible numbers. We're trying to put them in nearly compatible number pairs. So we're looking to group two numbers together, in this case, that are approximately 100 when you add them together. And the groupings are not always the same. For example, Brooklyn might choose one grouping that's just as reasonable as Dana chooses, and everybody's going to be good with it, okay? So your estimation doesn't necessarily have to match my estimation. There are things that can certainly make that estimations wrong, but there's also multiple ways that they could be right. So what pairs of numbers might you group in this particular list of numbers?
42 and 64.
Okay, that sounds like a reasonable one, 42 and 64. Anything else you might group? 35 and 71. I think those are maybe a little closer to 100. Sure. So that's another 100. Yeah. So 100, 100, and then if you even want to change the 50 and 5 in the middle to say that it's approximately 50, go for it. It's okay if you leave it 55. That's fine too. I don't know that either's right or wrong. It's just a different way of doing it. And so we end up with approximately 250 or 255. Somewhere in that ballpark. Now 42 and 64 is actually over 100, so you might have chosen to group the 42 and the 55 together. Those are approximately 100 too. So there's more than one grouping that sometimes works with the numbers we're given.
Whenever we're doing homes like this, we might all have different answers.
You're not going to all have different answers because there's only so many ways to do the grouping, but there might be several answers that are different but all right.
Okay.
So yes, there is a possibility for that. Sometimes there's a more natural grouping, so it might be, like 3/4 the class does one thing, all the same even. So. Okay, 3 more strategies to look at, and then we're done for today. The first one of the last 3 is called clustering. So just like other strategies, some methods work better given some sets of numbers. Clustering is a strategy that works really specific cases. So in particular, clustering works nicely for this set of numbers because they're all fairly close to the same very nice number. What? What number are all these numbers pretty close to? They're pretty close to 500, right? Yeah. So each of these numbers is approximately, some closer than others, but each of these numbers is approximately 500. So clustering says they're all sort of grouped up around 500. That seems to be a reasonable approximation if I were to round all of them to the same thing. Well, okay, so it means I have 5 numbers that are worth approximately 500 each. And with some multiplication, I can quickly say that that's approximately 2,500. All right, so you can obviously see that that's a very limited strategy. When it works, it's great, but it doesn't always work. Okay, rounding is another one. So with rounding, especially when they don't give you anything, you get a lot of freedom. So you can decide how you want to do the rounding. So for instance, you might want to round to the thousands place. Or maybe you decide that it's more appropriate here to run to the hundreds place. It doesn't tell you, so I'll do both just for the sake of seeing it for you guys twice. But if it doesn't tell you, you just get to pick and you just do 1 and move on. You don't need to do 2. So as you remember, if we're rounding to the thousands place, we look in the hundreds place to decide if we're going to round up or down. 5 and up, I round up. 4 and down, I round down. So the number 4789 is either 4,000 or 5,000 because that's the 2 numbers that are on either side of 4,789. And the right number is 5,000, right? And the real reason is because 4789 is closer to 5,000 for 4,000. But if you're thinking more of like a step-by-step, it's because the 7's bigger than 5, and that's the next digit. So if we do the same thing with the 3148, it's between 3,000 and 4,000. It's closer to 3,000. So this is approximately 8,000. The hundreds place, if you wanted to look at the hundreds place, you would simply look at the 8 and the 4 instead, right? So 4789, so it's either going to stay 4,700 or it's going to go up to 4,800. So if 89 is the end, it's going to go up because the 8 makes it go up to 4,800. And then 3148, the 4 makes it go down, so it will go down to 3,100. And then adding those together, we would get 7,900 approximately.
Does it change the... I got another page. Does it change the thousands place?
No. Thousands place stays the same because I was rounding to the hundreds place. I mean, it could change the thousands place depending on what the numbers are, but it didn't in this problem.
Okay, that makes sense. So it doesn't carry.
Yeah.
Sorry. I thought we were like carrying it over from the...
No.
I was like, what?
No. Okay, so that's rounding. And the last one's actually using the range, which feels somewhat like silly, I understand, but it's actually super practical, and you guys do this all the time, whether you're aware of it or not. A range is really just a set of values that you're saying my answer has to lie between these numbers. So I was kind of using it over here already. I was saying, hey, look, 4,700 and something. That's really between 4,000 and 5,000, right? Well, that's all range is. Range is looking at the numbers and saying, I'm between this number and this number. And so again, the range is usually done with just the one number at the beginning and then you zero things out after that. So what you do is you take the number 300 and you do a number one higher, or up from that and down from that. So 370 is between 300 and 400. So you round down, you round up. And then the 647 is between 600 and 700. Okay, round down, round up. And then as you add these together, you're going to get 900 and 1100. And so your range is 900 to 1100. And one of the places you probably do this without sort of realizing it is you do it when you shop a lot. You sort of have in your mind a perspective idea of how much something should cost. And if it's too low, you start to wonder, is the product good? If it's too high, you start to say, out of my budget, right? You put a range on values all the time when you do things. So this is range. Any questions on that?